Hi, my name is Jiwon Seo, and I'm an associate professor at Hanyang University, Korea. Let me present SAGE, a system for uncertain network analysis. Many networks have uncertain structures or probabilistic connections. Protein interaction networks, for example, are constructed from experimental analysis, so their connectivity is probabilistic. These uncertain connections make it harder to understand the networks. In this small network, for instance, finding reachable or non-reachable vertices from this source vertex in red is pretty straightforward. But if the connections are probabilistic like this, where this value here means with 70% probability the edge exists, and with 30% probability the edge does not exist, then it doesn't make sense to find reachable or non-reachable vertices from the source vertex. So the problem should be changed to find top k most reliably connected vertices from the source vertex, and this is a fundamental problem in uncertain network analysis. The standard algorithm for this problem samples a number of possible networks and check if a vertex is reachable in each sample network, and then count the number of sample networks that the vertex is reachable. Then we find k vertices with the highest count. In fact, this pattern is very common in uncertain network analysis. They sample possible network instances, run analysis on each sample network, and aggregate the analysis result, possibly repeating the step 2 and 3 multiple times. This actually requires considerable engineering effort because we need to maintain a large number of sample networks and run analysis on them for more accurate results. That means we need to manage the memory overhead of keeping those sample networks, the computation overhead of processing them, and the storage overhead of storing billions of vertex attributes in those sample networks. Existing graph systems do not have the programming model for this, nor do they provide optimizations to reduce this overhead. To ease the difficulty of uncertain network analysis, we propose SAGE, a disk-based system for uncertain network analysis. SAGE provides a programming model that can express sampling-based uncertain network algorithms. It supports domain-specific optimizations to minimize the memory, storage, and computation overhead. I'll explain the programming model first, and then these 4 system components. In existing graph processing systems such as Pregal, vertices in a graph are marked as active or inactive by the running algorithm. Then the system goes over the active vertices and runs their scatter operations, which send messages to their neighbor vertices. Next, the system delivers the messages by running gather operations that update the target vertex attribute and optionally activate the vertices themselves. SAGE runs in a similar manner, but it performs the scatter and gather operations in all sample networks, as shown in this figure with 5 sample networks. In SAGE, we do not materialize the messages due to their large overhead, but instead mark the receiving vertices as triggered in a bitmap. After running scatter and gather for all sample networks, we perform vertex-wise aggregation and then global network-wise aggregation of the analysis results. For the analysis of sample network, we provide vertex class as the interface representing a vertex in a sample network, and for the aggregation, we provide G-vertex class representing a vertex in the given uncertain network. The paper has more details on how the programming model enables our optimizations. Let me show you how top-k reliability search is implemented in SAGE. The algorithm performs these 3 steps. The first step is implemented in top-k vertex class, marking reachable vertices in sample networks. Then we count the number of sample networks that each a vertex is reachable in vertex-wise reduction function. Finally, we perform global reduction to find k vertices with the highest counts. Now I'm going to explain these key system components, starting with the edge computation executor. Existing graph systems typically have active vertex bitmap in memory for efficient processing. And Sage has similar structures, but it maintains 3 bitmaps for activation, triggered, and triggering status of vertices. We also have sample network bitmap for each vertex stored in SSD for activation and triggering status of the vertex in sample networks. With the vertex bitmap in memory and sample network bitmap for each vertex in SSD, Sage can efficiently and correctly perform edge computations, running scatter operations using the vertex bitmap and sample network bitmap, and triggering within scatter, then running the gather operations, and activation within the gather operations. The next component is deterministic sampler. To maintain sample networks, a previous technique keeps a sample network bitmap for each edge. For instance, for this edge from V5 to V6, since we have 5 sample networks, we have a bitmap of size 5 like this, and for each edge we have similar bitmap. This compactly stores sample networks, but still the overhead is really large, for example requiring 18 terabytes for storing 1 million sample networks. To minimize this overhead, we exploit the property of pseudo-random number generators that generate the same sequence of numbers when given the same seed. For edge S to T, we set the seed value based on vertex S and T, and then resample edge existence as scatter and gather execute on that edge. For example, for this edge from V5 to V6, we set the random seed like this, and then regenerate random numbers to obtain edge existence bitmap shown here. This technique eliminates the memory overhead at the cost of small CPU overhead. To verify that our approach is statistically sound, we conducted KS test, and for different graph ordering, and hash functions, we confirmed its soundness. Let me briefly explain the hybrid gathering component. Because of the structural similarity of sample networks, many of them have exact same vertex attributes, and for such cases, we perform exact same edge computations redundantly. To reduce the memory overhead and redundant computations, we design a bitmap-based data structure that enables sharing attributes between sample networks. This saves memory, storage, and redundant computations. But this bitmap-based data structure may not be optimal if vertex attributes become diverse, so we dynamically switch between this value-sharing data structure and non-sharing one and perform gathering operation accordingly for our edge computation. Lastly, I'm going to explain vertex cache. When we execute gather operations, we need to fetch source and target vertices from disk, and those vertices may be later accessed in future gather operations. As the cache size is limited, we need to determine which one to retain in the cache. The optimal caching policy is to evict those that are accessed furthest in the future. To make that possible, we schedule the gather operations exactly ordered by the target IDs and make future vertex access predictable. In this graph, let's say gather operations are requested for the red edges. In this timeline for gather operations, where Ti corresponds to target vertex Vi, we order the edges by the target vertex and execute the gather operations in this order. For optimal caching, we set the priority of a vertex in the cache to be the negative of each future access time, so that the further away each future access is, the lower the priority is. After the gather operation of this edge here, V4 is accessed as source of gather at T5 or T6. As T5 is sooner, we update its priority to be minus T5. For the evaluation of SAGE, we used 8 representative uncertain network algorithms and 6 real-world networks. We also used large synthetic networks for the scalability evaluation of SAGE. We evaluated these 3 system settings. The baseline is SAGE without our optimizations. It implements the state-of-the-art uncertain network analysis system. SAGE MEMOpt is SAGE with all optimizations, and thus it uses smaller amount of memory compared to the baseline because of deterministic sampling and hybrid gathering. SAGE XOpt is SAGE with all optimizations, and its vertex cache size is increased so that it consumes the same amount of memory as the baseline. First, we show you the memory efficiency of SAGE MEMOpt. We measure the memory consumption with increasing the number of sample networks from 100 to 100,000. You see that SAGE uses much smaller amount of memory across all algorithms and datasets. And it uses only 1 to 60% of memory compared to the baseline. Now let's see the performance gain of SAGE over the baseline. This figure shows the speedup of SAGE MEMOpt and SAGE XOpt over the baseline system. SAGE MEMOpt is up to 6.8 times faster when using only a fraction of the memory compared to the baseline. And SAGE XOpt is up to 14 times faster using the same amount of memory as the baseline. The baseline ran out of memory for some experiments marked by gray filled boxes, and as SAGE XOpt uses the same amount of memory, it failed to run for those cases as well. But for SAGE MEMOpt successfully executed for all those cases, demonstrating its memory efficiency. For the COG dataset with shortest path algorithm, SAGE XOpt runs 10% slower than the baseline. This is because COG has many edges with low probability, so the overhead of deterministic sampling is high. That is, when we resample the existence of an edge, if the edge is not connected in all sample networks, then gather need not be executed at all, so the resampling time is wasted. So let's look into this overhead of deterministic sampling now. For that, we deployed the technique to a subset of the edges, with the rest edges stored in a bitmap using more amount of memory. We measure the memory usage and execution time of the algorithms. This shows the memory usage of the algorithms. When we deploy the technique to more edges, the memory usage is reduced. For YouTube network YT with KNN and KCO algorithm, the reduction is relatively small because their vertex attribute size is very large. Now let's see the execution time. For the YouTube network denoted by YT, the overhead of deterministic sampling is not large, especially for KNN and KCO that have relatively large computation overhead. For COG, the overhead is larger because of the low edge existence probability that I mentioned a few slides ago. If deterministic sampling has relatively large overhead, as in the COG network case, we can apply the technique to a subset of edges and control the trade-off between execution time and memory overhead. For more evaluation result, please read the paper. Let me summarize. We proposed SAGE, a system for uncertain network analysis. It provides a programming model that eases the difficulty of the analysis and implements domain-specific optimizations. Compared to the baseline, Sage uses 23% of memory but runs 2.7 times faster. Thank you.